Good afternoon to everyone. I welcome all of you to the 65th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, India, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Dr. Kevin Zilasa. Dr. Kevin Zilasa has obtained his PhD from the Center for Research and Advanced Studies of the National Polytechnic Institute, Mexico, in the year 2019. He then continued his postdoctoral work for 1.5 years at Center for Mathematical Research, Montreal, Canada, which is one of the premier institutes for theoretical physics and applied mathematics in the world, and carried out another postdoctoral work at the Department of Theoretical Physics, Nuclear Physics Institute, Prague, Czech Republic. Dr. Zilasa's research interests focus on quantum theory, in particular in the study of systems beyond conventional quantum mechanics, such as non-Hermitian Hamiltonians with PT symmetry and non-PT symmetry, open systems modeled through time-dependent Hamiltonians, and position-dependent mass models constructed through geometrical deformations. As an extension, his research finds applications in quantum optics, electromagnetic traps, and the study of dissipative systems. Today, he is going to talk about time-dependent quantum systems. With this short introduction, now I invite Dr. Zilasa to deliver his lecture. Over to you, Dr. Zilasa.
Okay, thank you very much for the nice introduction. I would just like to double check. Can everyone see my screen?
Yes.
Okay, perfect.
Can you move? Yeah, so that we can. Yeah, it's moving. Yeah, perfect.
Oh, perfect. Okay. So, well, thanks for the introduction. And yes, today I'm going to talk about some of my recent results in time-dependent phenomena in quantum mechanics. As most of you might know, well, the main tool for non-relativistic quantum systems is, or the dynamical law, is the Schrodinger equation. And well, this is even in the stationary case, is a bit challenging to solve, even for some realistic models. So today I'm going to talk about some techniques that we use in order to design some quantum potentials or quantum Hamiltonians, such that the information, such as solutions, eigenvalues, and so on, are exactly obtained. So today I will focus my talk in two ways. First, I will introduce some basic notions about stationary quantum mechanics, just to remind some basic ideas. And then I will start introducing how to address the problems when the potentials are dependently on time. And as you might see, mathematical apparatus becomes much more complex to solve, but still we have some tools in order to address these problems. So, well, as I say, I will, roughly speaking, split my talk into stationary solutions and time-dependent phenomena. So before going through all the calculations, it is always interesting asking why, right? I mean, why are we so interested in solving this class of equations? And well, we might notice that this Schrodinger equation is not exclusive for quantum systems. And it turns out that there are several other physical systems that they fulfill a dynamical law, which is mathematically speaking equivalent to the Schrodinger equation. One of these examples, for instance, on top of these two pictures, I'm presenting some quantum models. I mean, this is to the upper left, we have this stationary oscillator, and these are the solutions. To the right, I have this, which is a generalization, which includes a potential, which is complex value. So this potential has real and imaginary part, but despite this, this class of potential has real eigenvalues. So this is the applications in quantum mechanics, but also here in the lower left panel, this is an optical system. And basically this black box we have here is an optical media that that emits some guided modes inside. And guided modes, I mean light, guided light. And this kind of system, when we analyze the electromagnetic field propagation, we realize that the dynamical law that these electric fields fulfill inside this medium is nothing but a Schrodinger-like equation. So solutions in quantum mechanics can also be directly applied to these optical systems as well. There are other classes of physical systems, for instance, periodic systems such as graphene or other periodic structures, which, well, they don't directly satisfy a Schrodinger equation, but they rather satisfy a direct equation. But when we decouple the equations in the effective direct equation, we arrive to a conventional Schrodinger equation. So this is why I'm presenting these 4 examples, because we can get a general idea of how solving one mathematical problem with some boundary conditions, we can apply this into different physical scenarios: optics, material science, quantum mechanics. So, well, with this motivation, I would like to roughly talk about stationary systems. So, as you all know, as I just mentioned, the dynamical law ruling non-relativistic quantum system is the Schrodinger equation. In this regard, I'm not considering minimal coupling. So in this case, I will have this relatively simple Schrodinger equation, which is nothing but a partial differential equation, second order under position, and first order in time. So this is the dynamical law, and B, in this case, is the potential. So if we are modeling any system, basically the information of the system, in this particular case, it's coded into the potential energy here, Bxt. Okay, so well, this is a partial differential equation. So it's most of the time it's a challenging task to extract solutions from here. But if we consider, for instance, a potential which only depends on the position, that means that Bxt is just a function of x. So we can see that this equation can be easily decoupled into an Sturm Liouville equation. And that's what we get in this equation in the middle. And this is the equation that appears in basically every textbook. Basically, we forget about the time-dependent Schrodinger equation, and we focus only on the Sturm Liouville problem. And the reason of this is, well, because the time evolution is just a simple phase. That means that the solutions to the Schrodinger equation can be obtained only by adding this linear phase on time. And when we are talking about, for instance, bound states, we need to impose some boundary conditions, which is that the wave function is square integrable. This is usually referred to as the solutions belong to L2 space, and L2 means precisely this definition I have below. So, well, this is basically the main apparatus to solve quantum systems, which are stationary. By stationary, I mean time independent. So here we only need to specify what is the potential, and we can get the eigenvalues here, which is E, physically speaking, is the energy, and phi, which is the wave function. For optical systems, this E is associated with the frequency of the guided modes in light. As you remember, in the previous slide, I presented this black box, which was an optical medium. So in the context of optics, this E plays the role of the frequencies. And phi plays the role of the electric field. So this is the analogous we have between quantum mechanics and classical optics. Okay, so here, well, we need to specify what is B, and well, we have some well-known examples in the literature. You can go to pretty much any textbook in quantum mechanics, and you will find at least the first 2 cases, which is the harmonic oscillator. We know the potential is x squared, which is parabolic. Oh, sorry. Eigenvalues are linear in n, so they are equidistant. And we also have the singular oscillator, which is defined on the half-real line, and they all are also equidistant eigenvalues. But we have some other more general systems, such as Poisson-Teller, which has this form, and the eigenvalues are also exactly well known. The same with the trigonometric counterpart of Poisson-Teller, and finally, Morse. This is not an exhaustive list. There are some more additional exactly solvable systems, but this is pretty much the most well-known that we usually find either in the literature or in the online articles. So this is this is a list, but solving the Sturm Liouville problem, for other problems beyond these models is actually a pretty challenging task. So we are usually limited on the class of models we can exactly solve. And of course, we can apply perturbation techniques and so on, but it is always desirable to have some tools in order to extract exact solutions. And in this regard, this is where the factorization methods come in. And basically, the factorization method is a technique that basically in which if we know one exactly solvable system, let's say the harmonic oscillator, we know the solutions of the harmonic oscillator, we know all the eigenvalues, we even know what are the non-physical solutions. So by using the factorization method, we can take the harmonic oscillator, make some deformations on it, and construct another Hamiltonian, which is also exactly solvable. And one of the advantages of this technique is that the new Hamiltonian is either isospectral, which means we can generate families of Hamiltonians that have the spectrum of the oscillator, or we can introduce additional eigenvalues. And this is pretty useful because we can do some spectral design by using these techniques. We can construct a new Hamiltonian that has the oscillator, the same eigenvalues of the oscillator, plus another eigenvalue that we can introduce at will. And another advantage of this method is that the new Hamiltonian will be exactly solvable. I will present here this particular example later. But, well, roughly speaking, as I say, when we have, in general, an eigenvalue problem, here H, which is known, and the goal is to get this H tilde and the eigenfunctions and eigenvalues for this new unknown operator H, or eigenvalue operator H. In general, well, I will assume that H, the solutions of the first Hamiltonian, which is already known, well, they span a complete vector space, which is if the initial problem is already known, well, we already have the vector space to work with. So the idea is the following. We have this H, which is known. So we propose two operators, A and A dagger. A dagger, of course, is the adjoint operator, provided that we have already defined the inner product. So let's assume that we have the inner product. So, and the vector space, as I mentioned here, H well defined. So we will introduce these two operators, A and A dagger, such that H factorizes in the following way. Here, epsilon is an arbitrary real constant. And the reason to introduce this A dagger A is to preserve the self-adjointness of the operator H, or the hermiticity, of the operator H. So by doing this, we can ensure that this operator H will be self-adjoint, because this is the main class of Hamiltonians I will talk today. This is strictly not necessary. We can even remove this condition, but for this talk and to make everything simple, I will focus on these Hermitian models. So we can introduce a new Hamiltonian H tilde, which is basically factorized by using the same operators A and A dagger, but the factorization order has been reversed as compared to H. And what's the point of doing this? Well, we have some properties if we do this factorization. First, we get what it is usually known as intertwining relations. And this is actually one of the main interesting properties of this factorization, because this means that this operator A is a mapping between the solution of H and H tilde. That means that the action of A is over eigenvalues of H will give us the eigenvalues of the new unknown Hamiltonian. So this means that we don't have to solve the new Hamiltonian. We only apply these mappings and we automatically get all the solutions of the new Hamiltonian. Okay, this is provided that we ensure all regularity conditions, which I will discuss later. But this is why this method is so powerful. Because if we manage to do this factorization, the new Hamiltonian is automatically solved. And next is the role that plays this constant epsilon. And it turns out that this constant epsilon is an additional eigenvalue on the Hamiltonian. So this means that we can fix epsilon at our will, and this epsilon, if the boundary conditions are satisfied, this epsilon will be a new eigenvalue of the new Hamiltonian H tilde, and this epsilon is usually an eigenvalue which is not present in the original Hamiltonian. So this means that H tilde will have this additional eigenvalue epsilon. This is roughly general. I haven't even said what's the form of H, which kind of vector space we're talking about. So I will introduce some simple examples, which I hope will illustrate this, and then I will go directly to the applications in quantum mechanics. So the first thing we can think is, for instance, matrices. We can think about 2 by 2 matrices. This is something pretty simple. So suppose that H is this diagonal 2 by 2 matrix, which is nothing but one of the Pauli matrices, right? So the eigenvalues of this matrix H are pretty straightforward because H is really diagonalized. So the eigenvalue, we know that this is a 2 by 2 matrix, so it must have 2 eigenvalues. They may be equal or different depending whether it's degenerate or not. In this case, it's clear that this matrix has 2 eigenvalues, 1 and minus 1. The eigenfunctions are simply this, and well, the eigenfunctions are normalized in the Euclidean, with respect to the Euclidean vector inner product, and they are orthogonal among themselves. So this is pretty simple, so there is nothing remarkable here. So let us introduce these operators A and A dagger that I just mentioned. So let's suppose that we have these operators A and A dagger in the following form, where A, B, C, and D are complex constants. So we implement the factorization you just presented in the previous slide, and we get the following matrix. If we revert the factorization order, we get the following matrix. Okay, but now H is already known. We already know what is H, right? It's this Pauli matrix here. So basically, by equating this matrix with the original problem, we have a set of equations for these constants A, B, C, and D. This element here is 1. This here, the second diagonal element, is minus 1, and the off-diagonal elements are 0. So basically, with this, we can establish what's the form of A, B, C, and D. And once we find what are these parameters, we can substitute this into the new matrix, and we will generate a new matrix, the eigenvalues of which are automatically 1 and minus 1. Because remember, the eigenvalues are preserved. So it means that it doesn't matter what form this matrix takes, the eigenvalues will be always 1, minus 1, and possibly epsilon, but I will talk about it in the next slide. So by solving this equation of system, which basically is equating this to the Pauli matrix, we get this system of equation. This is pretty simple to solve, and we will get the A, B, C, and D in general. They have this form. So after doing some calculations, well, we get these quantities, and we get the new matrix H tilde, and H tilde is given by this matrix. So you may notice here that basically what I did here, or what I got from the factorization, is nothing but a rotation. Basically, by doing the factorization, I got another matrix which has the same eigenvalues, 1 and minus 1, and this new matrix here, it can be easily seen as a unitary transformation of the Pauli matrix. So this is a simple example. This is nothing remarkable, but this is a nice example of how we can get new Hamiltonians departing from one which are already known. We can do some calculations here, for instance, and analyze what happens to epsilon. And well, it turns out that epsilon can be doesn't lead to any linear independent solutions, and this is expected because this is a 2 by 2 matrix. So we cannot include an additional eigenvalue because of the dimension. We have at most 2 eigenvalues, 1 and minus 1. That's it. So this is a simple example with 2 by 2 matrices. But what about 2 by 2 and 3 by 3 matrices, for instance? So So this is another possibility where epsilon plays an interesting role. So if now we introduce the following factorization matrix A and A dagger, which is not in a square, notice that this is not in a square matrix, but the product of A and A dagger are indeed the square matrices, right? So if we do the same factorization, we see that this multiplication, or this factorization, sorry, gives me a 2x2 matrix, and the new unknown matrix is 3x3. Okay, so we are this initial matrix is known, is the Pauli matrix again. So I get another set of equations, which is given here below. Oh, sorry, I will hide this. So, and now we can define what is A, B, C, D, E, and F. And with this, we can generate new matrices. Now take a look at this. This is a 3x3 matrices. So we know that this must have 3 eigenvalues. It can be distant, it can be equal, the matrix anyway, but it must have 3 eigenvalues. And this is where epsilon is important, because from the factorization method, we know that this matrix will have automatically 1 and -1 as eigenvalues. But what is the third eigenvalue? Well, in this context is epsilon. This constant epsilon that we just introduced will be the third eigenvalue of the new matrix. So by doing some calculations, and I mean, this case is a little bit more complicated, so I will impose some simple constraints. For instance, what happens if B is equal to 0? You can do the calculations, it's not so difficult. If you consider B different from 0, but B equal to 0 is a pretty nice illustrative example. So by using B equal to 0, we get the exact form for A, C, E, F, and G. And well, we can substitute this into the new matrix H tilde, and well, H tilde has this form. And the remarkable thing of this matrix is, again, I don't need to solve the eigenvalue problem for this matrix. I already know that the eigenvalues will be 1, -1, and epsilon. And what about the eigenfunctions? Well, as I say at the beginning, the eigenfunctions are just mappings. If I have the eigenfunctions of H, I only have to apply A, and this will give me the eigenfunction for the new matrix H tilde with the eigenvalue +1. If I do the same with, oh, sorry, this must be minus here. So if I apply this to the phi minus, I will get this solution, this vector, and this vector is the eigenvector with the eigenvalue -1. And lastly, the eigenvector associated with epsilon is this one. So notice that here, instead of solving this 3x3 matrix, basically I'm spectrally designing this new matrix. If I want, for instance, epsilon to be -10, well, I just fix epsilon equal to -10, and I have a matrix that has these 3 different eigenvalues. Here, I would like to remark that this is an example, and you can actually make it even more interesting. You can start from a diagonal matrix, which is epsilon1 and epsilon2, where the epsilon1 and epsilon2 real arbitrary. And you can do all this procedure and get a non-diagonal matrix, which will have the eigenvalues epsilon1, epsilon2, and epsilon. And the procedure is pretty much the same. So, and again, you may be asking, well, this is a 3x3 matrix. I mean, this is not so complicated to solve, even if I try to diagonalize this matrix. And yeah, you're right. But the interesting thing in this is that you can iterate this procedure. So you can start from a 2x2 matrix, do this procedure, include a third eigenvalue, then you can apply the same factorization, include another eigenvalue by increasing the dimensionality of the matrix, and you can continue so. In this way, basically, you can construct any matrix with the eigenvalues that you want. And you, in the end, you only start from a simple 2x2 matrix. And this is why this method is so versatile. It's so simple, elegant, and we can do so much with it. Okay, so enough about matrices. So now, how do we implement this into quantum systems? Well, as I say at the beginning, for stationary systems, we have the Sturm Liouville problem, right? So for the Sturm Liouville problem, we have this, the vector space is different. It's no longer matrix. Well, we already know that the vector space here is the space of solutions that belong to L2. So the operator H is now a differential operator, and it's a differential operator of second order. So for the harmonic oscillator in particular, this is the Hamiltonian, these are the eigenfunctions, and these are the eigenvalues. This is a textbook problem, so I mean, this is a pretty well-known system. Okay, so let's apply the factorization method to this operator. It is quite intuitive, right, that if this is a second-order operator, the factorization operators should be of first order. So this is what I introduce here. We can introduce this operator A and A dagger such that they are first-order operators, and they have this unknown function beta. You might be asking why I didn't include a factor here next to the derivative, but we can include such a factor, and in the end, we will realize that such a factor must be equal to 1. So that's why I'm not including here, but if you are wondering why, well, you can double-check the calculations, and you will see that in the end, you will arrive to this. So to make the notation simpler, I just consider this. Beta is a real value function. So if I factorize H, this new harmonic oscillator Hamiltonian, by using the same rule I said at the beginning, we get the following equation. And here you can see that we have the double derivative and all this remaining part. This remaining part should be equal to the harmonic oscillator potential x squared, right? So from here, we get a differential equation for beta. That means, and in order to get beta, we need to solve this differential equation here. Once we find what's the value of beta, we can reverse the factorization and get the new potential B tilde. And remember, B tilde, we don't know what is it, but if we succeed on getting beta with the proper boundary conditions, the eigenvalues of this new Hamiltonian H tilde will be exactly the same as the harmonic oscillator. That is, H tilde will have eigenvalues equal to m plus 1 and potentially epsilon. I will talk about it in the next slide. Okay, so you may be asking, well, but now the price to pay is that beta is a nonlinear equation, right? We can see here that beta is nonlinear. Here, prime stands for derivative with respect to x. Sorry, I forgot to mention. Beta prime is the derivative of beta with respect to x. So, well, we have to solve this nonlinear equation. Fortunately, this nonlinear equation is pretty well known, and this is the Riccati equation. And one of the features of the Riccati equation is that it can be easily linearized. So even though it's nonlinear, we can easily propose an ansatz to linearize this equation and solve another linear equation. I would like to remark that this idea in this simple way I'm presenting was originally introduced by Mielnik. There has been several other works about factorization, but in this paper of Bogdan-Mielnik in 1984, he introduced this idea in a pretty simple way that is quite clear to understand. So anyone interested in more details, I will refer them to this reference, which is, I mean, it's 2 pages long paper. Anyone who knows the basic concept of quantum mechanics can understand this. This is the beauty of this paper, that is so simple and is so powerful. Okay, coming back to the Riccati equation. We have beta, right? So as I mentioned, it is quite straightforward to linearize the Riccati equation. And if we introduce this ansatz, beta equal to u prime over u, if we substitute this beta into the Riccati equation here, you do the calculations, and you arrive to this equation here for u. Okay, so you might be asking or you might notice that this new equation is nothing but the harmonic oscillator eigenvalue equation, right? We have double derivative x squared times u equal epsilon u. Okay, so this is why we need an exactly solvable model to begin with, because if we know all the solutions, physical and non-physical of the initial system, basically this equation is already known. And here, epsilon needs not to be square integrable, because notice that epsilon, u is not an eigenfunction neither of H, the original Hamiltonian, nor the new Hamiltonian H tilde. So basically, u can be a square integrable or may not be a square integrable. It doesn't really matter. So for this particular differential equation, for arbitrary epsilon, The solutions for any arbitrary epsilon are given here below. In this case, 1f1 is the confluent hypergeometric function. This is one a particular case of the Gaussian hypergeometric function. And this function reduces to the Hermite polynomials on the particular limit, reduced to Laguerre polynomials under another particular limit, and so on. But in general, for any epsilon, this is the most general solution. Remark that this is a second-order differential equation, so we need two linearly independent solutions, and those linearly independent solutions are this one given here. Okay, so a word of warning here. Notice that beta is u prime over u. So we must be careful when we choose u, because if u has any zeros or any nodes, beta will be a singular function. If beta is a singular function, b tilde will be singular as well. And we don't want to deal with singular potentials unless the original system has a singularity at the same point. This is the only condition. But here, this is the harmonic oscillator, and this doesn't have any singularity. So we must avoid any singularity of beta, and therefore, u must be different from 0. But this is pretty easy to get because the confluent hypergeometric function is well documented. We already know the zeros distribution. I mean, we cannot say exactly where the zeros are, but we can count the number of zeros, and we can find the conditions in general such that this linear combination never has zeros. And this is pretty easy to do. So this is the only warning we must take here. And well, if we substitute this u into this beta and we get a new potential, well, after doing some calculations, we get that the new Hamiltonian H tilde will have this potential V tilde, V tilde will be of this form. It's the x squared, which is the oscillator, plus this deformation, which is logarithm derivative. Okay, so we already managed to get the new potential. What about the eigenfunctions? Well, the eigenfunctions are simply mappings, as I say. So these phi n are the eigenfunctions of the harmonic oscillator, you know, the Gaussian times the Hermite polynomials. So by doing this simple algebra, we get the eigenfunctions of the new Hamiltonian H tilde. And the eigenvalues are, associated with these eigenfunctions are 2n plus 1. Additionally, we have a new eigenfunction, which I call phi tilde epsilon, which is nothing but 1 over u. And remember, u must be different from 0 in order to get a regular beta. So if u is different from 0, this phi epsilon is also free of singularities. So if in order to determine if this state is physical or not, we must ensure that this is a square integrable. And given the asymptotic properties of these hypergeometric functions, this is quite easy. So basically, this, if epsilon is less than -1, this and lambda is chosen appropriately, so this eigenfunction will be a square integrable, and well, we will have this additional eigenvalue epsilon. Again, I will insist here, epsilon should be less than 1, equal or less than 1, and 1 is the ground state of the harmonic oscillator. And if we do so, basically we generate a new potential. And if we would like, for instance, a harmonic oscillator-like potential with an additional eigenvalue of, I don't know, -pi, for instance, you want an additional eigenvalue of -pi. So you just fix epsilon equal to -pi, do the calculations, you get the potential, and the solutions are just given for free. You don't have to solve the new differential equation because everything is just mapped from the original problem. And this is where the beauty of the problem arises. And as I say, with the matrices, you can iterate this procedure. So you can, in one step, you can add one eigenvalue, you can iterate the procedure and add second eigenvalue, third, fourth, and so on. So, for instance, you can take the free particle system, which is, we know the free particle doesn't have any bound states, right? So we can apply the same technique, include one eigenvalue, then include in the second step a second eigenvalue, and so on. So you can construct from 0 a new potential with a spectral design that you want. This is why this technique is also called as a spectral design technique, because you can design the operator with the eigenvalues as you will, again, assuming that all the boundary conditions are properly satisfied. which in most of the cases is easy to do. Okay, so this is just a summary of this is the spectrum of the initial harmonic oscillator. These dashed lines is epsilon, and this energy epsilon in H is not physical because, as I say here, this is the eigenfunction associated with epsilon, and this in general is non-square integrable because these functions diverge asymptotically. So for the original Hamiltonian, this epsilon is non-physical, but the new H tilde is such that this epsilon is indeed square integrable. And we can go back and forth between the two Hamiltonian just by using these mapping operators A and A dagger. A takes me from H to H tilde, and A dagger does the converse. It is worth to mention that A dagger is not the inverse of A. I just want to clarify. I mean, these are inverse mappings, but A dagger is not the inverse. So this is something to take into account. But it doesn't matter. In the end, it only adds a constant. So they are proportional. The solutions between the two spaces are obtained by these mappings up to a constant, which is irrelevant in the end. So, okay, this is how it works. And this is how, for instance, a nice example, when epsilon is equal to -1, is another isospectral Hamiltonian because the harmonic oscillator has equidistant eigenvalues from 1 and so on. So I include a 1 and -1. I mean, I can include it whatever I want as long as it's less than 1. So here, this is an example. This red curve is the shape of the new potential. And these are the eigenfunctions of the new potential. This green line here is the original harmonic oscillator Hamiltonian, so we can see how it gets deformed by the how the new potential is deformed by the factorization method. The blue line is the same, but it's a parity invariant. So basically, both the red and the blue lines are equivalent up to a parity transformation. So this is the potential, and these are the eigenvalues, and again, the eigenfunctions, and again, the eigenvalues are automatically obtained. Okay, so this is how, in stationary systems, this is how we manage to, to do this spectral design. But the question here, and this is something I asked since I was a master PhD student, is how do we implement this into quantum systems that depend on time? And there is a main problem when we deal with time-dependent problems because, in general, we don't have an Sturm Liouville problem. Remember that the Sturm Liouville problem arises because the potential of the Hamiltonian, in general, does not depend on time. So we can separate the Schrodinger equation into a Sturm Liouville problem. But if the Hamiltonian depends explicitly on time, that last step is not longer valid. So we need to look in another way how to implement these ideas. And this is what I'm going to talk in the second, now in my second part of my talk. And this is the main topic of my talk. I will speed out a little bit. First, before going into anything related to time-dependent, this is I would like to introduce a pretty simple and nice example of how difficult it is to solve exactly a time-dependent Hamiltonian in relativistic quantum mechanics. And the best example, I think this is the most well-known example in quantum mechanics, is the parametric oscillator. The parametric oscillator is nothing but an oscillator. You can see here a conventional oscillator whose frequency depends explicitly on time. Here, I don't need to say what's the specific form of the frequency. I will just say it's a real value function, arbitrary, I don't know what is it. Okay, so it is clear that if I substitute this into the Schrodinger equation, I will not be the separation of variables that I made before to get the Sturm Liouville problem is no longer valid. So let's forget about that. There is no way we can do it. So the question is, how do we solve the partial differential equation associated with this Hamiltonian? Well, in the 70s and late 60s, Lewis and Riesenfeld presented a pretty, in paper, it's a simple idea on how to solve the related Schrodinger equation. And basically, what they realize is that if we find a constant of motion of the system, and by a constant of motion, I mean an operator, a linear operator I, that fulfills this equation. this operator I is such that the expectation values will be always time independent. It doesn't matter what solution of the Schrodinger equation you use, the expectation value of I will be always time independent. This is where actually this equation comes from. Basically, we impose that the expectation value of I is time independent, so we do some calculations and we arrive that I must satisfy this equation. So if we somehow manage to find this I, it turns out that we can prove that the eigenvalues are time independent. We can prove that I satisfies an eigenvalue problem with eigenfunctions that in principle depend on time, but the eigenvalues do not depend on time. The eigenvalues are time independent. So we can translate the problem from H to the quantum invariant, and we can solve the eigenvalue problem in the quantum invariant. But now the question is, okay, the eigensolutions of the quantum invariant are not necessarily solutions of the Schrodinger equation, and that's indeed true. But we can do some simple calculations and prove that our solution to the Schrodinger equation, which I call phi, is nothing but the solution phi times a complex time-dependent phase. And by doing some calculations, this phase must be computed for this relation. And if we do so, this psi is a solution to the Schrodinger equation. Okay, so here I would like to highlight three important things. I put it here in blue. Well, it was deliberate, actually. We need, if we have this time-dependent system, we need three different ingredients. First, we need to find the quantum invariant, which in most cases is pretty challenging to do. Second, if we somehow manage to get this quantum invariant, we need to solve the eigenvalue equation associated with it. So this is another step of complexity in the problem. And lastly, we need to find the phase. And this phase, we have to compute these expectation values. And well, this is an additional calculation we must do. So compared to the stationary system where we only need to solve this eigenvalue problem for the Hamiltonian, now for time-dependent system, we have to do three different things. Okay, in this paper, Lewis and Riesenfeld, they managed to do everything for this parametric oscillator. They found the quantum invariant by using some clever ansatz, which, well, when we read this paper at the first time, those ansatz are not so clear, but after doing some calculations, one managed to figure out what's going on. But well, this is one step. So we find this quantum invariant. Then we have to do several change of variables, and we solve the eigenvalue problem. And lastly, we have to solve this integral, most of the times numerically. And with doing this, we solve the parametric oscillator problem. Okay, so in the next slide, I will present a simple method to get all of this information for free. Basically, we only need to take the harmonic oscillator system. We will do some geometrical deformations, and we will show that all of these quantities I, phi, and chi can be obtained directly from the stationary harmonic oscillator by doing some clever geometrical transformations. And this is precisely the next part of my talk, point transformations. So again, the idea of this is to solve the previous Hamiltonian, but I will make it a little more general. So we will depart from this Schrodinger equation, which is in the second line, sorry. And this is nothing but the Schrodinger equation for the harmonic oscillator. Y is the spatial coordinate, tau is the time parameter, and well, we already know how to solve this. So we don't have to deal with this. We know the solutions for the harmonic oscillator, nothing new there. Okay, so the goal of this transformation is to find a Schrodinger equation like this one in the fourth line, such that it has this profile. We have a time-dependent mass and a time-dependent frequency. And the idea is to connect these two equations. How we do so? Well, we assume, first, Y and tau are independent. Because in non-relativistic quantum mechanics, position and time are not related among them. So Y and tau are completely independent among themselves. But we will assume that Y is a function of x and t, and tau is a function of x and t. And x and t are position and time, respectively, of the new Schrodinger equation. X and t are independent among themselves, but Y might depend on x and t. So this is the kind of deformation. You can see here that basically what I'm doing is if I have x and y and t, like a coordinate axis, x and t is basically a deformation of this rotation axis. And by doing so, I will now define the Schrodinger equation in this new coordinate system. I will assume that psi, a capital psi, is a function of x and t and also lowercase psi. And lowercase psi, sorry, is the solution to the new Schrodinger equation. So this sounds a bit complicated, but it's actually easy. This is I'm just reparameterizing the original coordinate system and the function. So, well, I will speed up a little bit. So by doing some simple calculations, for instance, how do we connect capital psi with a lower psi? So we do these operations here. These are total derivatives. So we have all these equations. I will not bore you with all the details because this is pretty straightforward. But what I really want to highlight are these terms in red. So, for instance, here you can notice that we get, in the first line, we get a relation between a partial of psi with respect to x with partial of capital psi with y and tau. So here you can really see how can we get the relation between the two systems. But there is a problem with the second derivative, and the second derivative includes no linear terms. And none of the Schrodinger equations we are dealing with have any such non-linear terms. Also, we have this additional term, which is a double derivative of psi with respect to time, and none of the Schrodinger equations in non-relativistic quantum mechanics has such a term. So in order to make the point transformation accordingly, we will have to assume that this term here, double partial of chi with respect to psi, is equal to 0, and the partial of tau with respect to x is equal to 0. In this way, we remove all the undesired terms. The latter just means the tau depends only on time, doesn't depend on x. That's what really implies. And the first condition basically says that k is linear on psi. And this is the condition. So, long story short, after doing this, we get this set of transformations. So by doing this and substituting it to the first Schrodinger equation, we will get something like this. This is here. So you can really see the shape of the Schrodinger equation. We have this term, double derivative on x. We have the first derivative, which we don't need, because if you remember, the Schrodinger equation we want to construct doesn't have any first derivative. So basically, this is 0. And we have a potential term, which has this form. Okay, so from here, we can really see some conditions. We impose that this term next to the double derivative of psi with respect to x, if we go back to the target Schrodinger equation, that term must be equal to h bar over 2n. So this term here must be equal to h bar over 2n. This term here equal to 0. By doing so, we find the following result. Y of xt must be linear on x with these time-dependent coefficients. This mu is just a parameterization of m because it's a bit cumbersome to deal with m, so I just introduced mu because it simplifies a little bit the calculations. And tau is given in terms of this new sigma function. Sigma is, well, basically given sigma, give a tau, or vice versa. If we give tau, we get sigma. This is just a convenient way to rewrite this equation. Okay, so if we substitute this into the potential, and we also fix this term equal to 0, we get the final result. And this is what is actually interesting. The new solution obtained by the point transformation is just given by this. This is the solution of the stationary oscillator. So we can see that basically what we're doing is we take the stationary oscillator, which depends on y and tau, and y and tau depends on x of t. So basically we are deforming the solutions of the original oscillator, but not only that, we are adding these time-dependent terms, mu and sigma. Mu, remember, is the mass, time-dependent mass. So we have to fix sigma, we have to determine sigma, I will say in a moment. And this A is nothing but a local phase, because you can see that this is a local phase because it depends on x. And well, these are minor details about the exact form of these functions, but what is really interesting here is that I'm only being substituting this term into the Schrodinger equation. And this is what we get without using any special assumption. Remember, the only assumption I made is vanishing these terms, but this is it was necessary because these are undesired terms, because we don't need it in the Schrodinger equation. So this is the only assumption we have made. Everything else is just a matter of calculations. And interestingly enough, if we obtain these functions, the new potential has exactly this form. This is a term x squared, x, and this is a term that depends only on time, not in x. So this is pretty irrelevant. So I will fix this equal to 0. Because in the end, this only contributes to a local phase. So this B0 is completely irrelevant. Okay, so notice that by fixing this equal to 0, we get an equation for gamma. And by fixing this equal to the parametric oscillator term, which is m of t omega squared, we get an equation for sigma. And in the end, well, sigma has this form and gamma has this form. So let us summarize what we have done. We introduce these geometrical deformations, we substitute, we banish all the nonlinear terms or the non-desired terms, and in the end, we arrive to this solution in the first line. And the only thing we need to solve now is the differential equation for sigma and gamma, and that's it. The problem with sigma is that sigma is a nonlinear equation, and well, it even looks more difficult than the Riccati equation. But it turns out that also sigma is well documented and is the Ermakov equation, and this has been extensively studied. So in order to give you some insight on how to solve sigma, for instance, this is sigma. Suppose that you have a linear equation, which is this equation equal to 0. So suppose that you have this linear equation. So if you have two linearly independent solutions to this equation, this must be equal to 0 here, equal to 0, there is a typo. So if you find two linearly independent solutions for this Q, so the solutions for sigma is simply this nonlinear combination, and that's it. And the only constraint is A, B, and C are arbitrary coefficients, which are bounded by this constraint. And notice that this is why we need linearly independent solutions, because if we use two linearly independent, this term here, which is the Gronskian, this goes to 0, and this leads to a singularity. So this is why we need two linearly independent solutions. If anyone is interested in the Riccati equation, which is one of the more useful nonlinear equations of physics, I would recommend reading this first paper, reference number 13, because this is an English translation from the original paper of Ermakov. And there are some other examples here, but this is a paper we published this year, so I will, if someone is interested in more examples, you can take a look at this last paper. Okay, so if we find two linearly independent solutions for Q, we find immediately a solution for sigma and for gamma, and that's it. So notice that here so far, we need to specify what is the frequency and what is the mass. And this is precisely what defines the interaction, right? We have a mass and we have a time-dependent frequency. So we fix whatever shape we want, as long as we can solve the linear equation. And basically, we find sigma and gamma, and that's everything we need to get the solutions for this new time-dependent system. So, and remember that, well, it's once we find sigma and gamma, mu is just the mass, so this is given. We find y, we find tau. This is an integral, but this is pretty easy to solve, actually, in general. So in this paper, we found an explicit expression for this tau. So you don't need to solve this integral. We only need to find Q1 and Q2, and this tau is also automatically obtained without solving anything else. So we find this sigma and gamma, we find y, tau, we only substitute this into this equation, and that's it. We have the time-dependent problem already solved by only knowing the solutions of the stationary system and solutions to the Ermakov equation. Okay, so now you may be asking, okay, how do we ensure that the solutions of the new time-dependent system are scored integral? Because we already know that the solutions of the harmonic oscillator are, but what about the time-dependent system? Well, you can do some calculations, and it's pretty easy to prove that the inner product is preserved. And this is a very powerful result, because it means that if you have a square integrable solution of this stationary system, the time-dependent system is automatically square integrable. The solutions of the time-dependent system are square integrable automatically. So you don't have to worry about whether or not it will be. And not just that, if the solutions are already normalized, the solutions of the new system will be also normalized. And this is the beauty of the method, because we already know everything about the oscillator. So we can just use that information to get the information of the new time-dependent system. Okay, another thing, another interesting thing. If you remember in the paper of Lewis and Riesenfeld, they found the quantum invariant, right? And I told you that they had to use an ansatz, and it was not so clear, and so. So it turns out that we can exploit the point transformation even more. And there is an interesting result in point transformation, and point transformations preserve constants of motion. And this is interesting because if we know a constant of motion of the initial system, we automatically have a constant of motion of the new system. And if you ask, okay, what's a constant of motion of the harmonic oscillator? Well, the Hamiltonian. The Hamiltonian is time independent and is by definition a constant of motion of the system. So if we take the stationary harmonic oscillator Hamiltonian and we do the geometrical deformations, we automatically get a new constant of motion of the new system. And well, I will not include the calculations. This can be found in my paper. I will give the reference at the end. But after doing some calculations, if you deform the harmonic oscillator, you will get this new operator I2. And this new operator is indeed the quantum invariant or constant of motion. Both terms are used interchangeably of the time-dependent system. And these functions which are here are the eigenfunctions of this quantum invariant such that they have this eigenvalue problem. So remember at the beginning I told you, you have to find the quantum invariant and solve the spectral problem. Here it's automatic. We only deform the Hamiltonian, we deform the solutions, and we know that the S eigenvalue problem deforms into this another eigenvalue problem. And so it's already done. So this is the solutions, and well, this is the invariant. And here, if we fix mu equal to 1 and gamma equal to 0, we recover exactly the quantum invariant that Lewis and Riesenfeld found in their paper. So here we only did these transformations, no ansatz required whatsoever. And well, this is a summary of the method. Basically, we depart from this stationary Schrodinger equation, we apply a point transformation, and we get the new system. But we can go even further. We can decompose this into the constant of motion and apply the point transformation and find the constant of motion of the new system as well, which is what I just presented. And remember, the last step I told you, Lewis and Riesenfeld say that we only need to find a phase as well, a time-dependent phase. Well, in this context, the time-dependent phase is nothing but this function tau of t, which is this integral, which is given here. And this integral, again, as I say, in this paper, is explicitly solved in general once you find Q1 and Q2. So that is given automatically by the transformation. So in this way, we complete this scheme and we can go back and forth. We can go from the Schrodinger equation, constants of motion, vice versa, and everything is close in this regard. Okay, so well, I'm running out of time, but I really ran out of time. So I would like to point out some potential applications. Remember, we need to solve this equation equal to 0. So there are here some references which you can check about some specific cases. For instance, the free particle case is actually one of my favorite ones. Because if we fix omega equal to 1 and mu equal, omega equal to 0 and mu equal to 1, the new time-dependent system is nothing but the free particle system. And basically what we get from the point transformation is a connection between free particle and harmonic oscillator. This is nothing new. This is something that has been studied, reported. It's even in the symmetries book of Miller. So this is nothing new, but this is just to verify that we recover, what is expected. So by doing this particular limit, we recover the relation between free particle and harmonic oscillator. In the other case, we can use the harmonic oscillator. And this is another interesting one. It's in the reference 16. Because if the frequency is constant and mu is equal to 1, it's interesting because the new Hamiltonian is time independent, that's for sure. But the quantum invariant is not. And this is something interesting because by doing this, we can find a family of constants of motion or the harmonic oscillator that depend on time, and they are not equal to the Hamiltonian. So this is why this second example, even though it looks trivial, a little bit absurd, is actually have some physical insight, because it provides us with these additional families of constant of motion that we usually overlook, because most of the time we don't need it. And well, we have another case, Caldirola-Canay. This is a problem that has been already solved by Caldirola independently and Canay. And in this paper in reference 17, I just presented how to use this in this context. And I also introduced a regularized version, because this Caldirola-Canay, when we compute expectation values, they tend to explode. For large time, the expected value of position or momentum, either of these two, they tend to grow indefinitely. So this is why in this case I introduced this regularized version, which is basically I'm just displacing the Caldirola-Canay, and this avoids me to getting these divergences. The only trade-off is that this problem is much more complicated and so, but it's still exactly solvable. And the last one is a smooth step-like frequency. This is basically a smooth version of the sudden approximation. If you remember in textbooks, we have a sudden approximation in which we assume that the frequency of the time dependence is instantaneous at a given time. So here, this is a frequency that it changes smoothly from one value to another. So basically, this smooths this sudden approximation. Well, this is not an approximation, this is exact. So in the limit when k tends to infinite, this is a step potential, a step distribution, sorry, and therefore we'll recover the sudden approximation in that specific limit. And this case is exactly solvable as well. So the details are given in the reference 18. And well, I ran out of time, so I would just like to point out some further applications. Remember that I started from the harmonic oscillator and I implemented these geometrical deformations, right? So we can apply this to other potentials, not just the harmonic oscillator. And for instance, we can start from this harmonic oscillator, implement a Darboux transformation, a factorization, which is the results I presented at the beginning of my talk. We can factorize, get this new family of potentials and this new Hamiltonian, and then we can implement the point transformation. So by doing so, we will get new time-dependent potentials, which are, they are usually called anharmonic potentials, indeed, but which will depend explicitly on time. And we will also get the quantum invariance or the constant of motion of the system just by doing what I did in the previous case. And just something simple, this is the new potential we get. And you may recall this pretty much the same as the one I presented before, but the difference here is that y depends on x and t. The new potential we generate is this B2, which is a little bit more elaborated. It depends. We have the parametric oscillator term here in the first term, but we have these other deformations. And the quantum invariant is just given by this here. So this is the constant motion of this new quantum system. And I will show you some nice pictures, for instance, of these anharmonic time-dependent systems. When the frequency is constant, we generate a periodic system on time. It's a potential that oscillates periodically on time. These are the solutions. Again, this is just a matter of doing some substitution by using the point transformation and the factorization method. So these are the eigenfunctions for different times. This is the potential in the first panel at different times, and these are the first three solutions equally at different times. And if we use this step-like potential I just mentioned, we can solve it analytically. It's a bit more complicated, as you may notice, because now it involves hypergeometric 2f1 functions, but still, this is another well-documented function. So we do the calculations and we get sigma, and this is the shape of the new time-dependent potential. Here, I just presented the density plot x as a function, x and t, the probability distribution for the first three solutions. And you can see that this is a system whose frequency is changing slowly on time, right? So you can see, maybe I won't have to plot for larger times, but you will see here that the wave functions are also oscillating, but the frequency of oscillations is also changing slowly on time. So it's adapting to the system continuously. So this is another class. Again, if you're interested in the exact expression, I'll give you the references. And lastly, the conclusions. we have presented this method of geometrical transformations and factorization method to enlarge the families of exactly solvable problems, both in the stationary case and the time-dependent regime. I would like to point out some recent results by Professor Andreas Frien and Rebecca Tenney. They published an interesting paper on how to extend this construction by considering non-Hermitian Hamiltonians. So this is, if someone is interested in time-dependent and non-Hermitian Hamiltonians, this is a pretty nice reference. And here, they actually exploited this, the fact that the constants of motion are preserved by the system, because in this construction in non-Hermitian regimes, we need this constant of motion. And they proved in the paper that they can get this constant of motion for the non-Hermitian system for free as well. So this is a natural extension. This is a pretty interesting result. We also published a non-Hermitian and time-dependent version of the Caldirola-Canai model, in which we found also, well, in this paper, we didn't discuss the constant of motion, but we presented the solutions as well. So this is another reference on how to extend into the non-Hermitian regime. Professor Frien and Rebecca Tenney, they just recently published this paper as a two-dimensional extension, which is also a pretty interesting result. So this is a further trending in this topic. Also, this construction can be extended to systems to PDM systems. PDM stands for position-dependent mass system, which means there are Hamiltonians whose mass depends on position. And lastly, this can be implemented to nonlinear system and even to relativistic direct equation. So, I mean, this is a broad topic. There are so many things to do, and there are so many things that can be explored. So, I mean, this is an open topic for anyone interested. And lastly, these are the references. If anyone wants to get a bit more insight into point transformation, I will highly suggest the second reference. It's pretty well explained, and it has nice examples, not in the quantum case, but they have pretty nice examples here. So if anyone is interested, the students, please take a look. So, well, that's everything for me. Sorry for using extra time, but, well, thank you for your time, and I'm open to any questions, please.
Thank you, Dr. Silasa.
Yeah, thank you.
So the forum is open for questions, clarifications, doubts.
Sorry. Yeah.
So questions from the audience. I'm not seeing any questions from the audience. Silasa, I have a couple of questions.
Yeah, sure.
Page number 13, 1-3. That's lambda, the second expression. Lambda is a constant or?
Yeah, sorry, I forgot to mention. Yeah, this is constant because remember the U is a second order equation. So we need a linear combination, right? And the linear combination, this lambda is the constant, basically.
Yeah. And then page number 24.
Okay, 24. Yes.
What is capital W and small w not is a constant, I assume. What is capital W?
Oh, yeah, sorry. Yeah, this is the frequency of the original oscillator. Yeah, this is what, sorry, my mistake. This is equal to 1 in this case, but this small W0 is, if you think of the harmonic oscillator, it has a constant frequency, omega 0 squared, right? Omega 0 squared, x squared. That's the harmonic oscillator potential. So this is the frequency of the stationary oscillator. But in this case, I consider it equal to 1. But yeah, sorry, this must be equal to 1 in this particular case.
Then page number 26.
Yes.
The third one, the Caldirola-Canai, is a damped harmonic oscillator.
Yes, it's the quantum version of the damped oscillator. Actually, Caldirola and Canai introduced this model in order to study damped phenomena in quantum systems, and this is why they introduced this time of quantum.
Do you have a Schrodinger equation for that damped harmonic oscillator?
Yes.
Do you have Schrodinger equation for this damped harmonic oscillator?
Yes, we have a damp, but one of the problems, and it's actually, it's a pity I didn't include the reference, but well, in the paper of Caldirola and Canay, they found something unusual because this is a damp oscillator, and we have this Schrodinger equation, but the solutions don't present any damping at all. And this is why this problem, Caldirola-Canay, has been so controversial. I have found reference from 10 years ago in which this is a heated debate on whether or not Caldirola-Canay in the quantum context is a damp system. So classically speaking, we get, the damp oscillator, but quantum speaking, we have the Schrodinger equation, but we don't have the damp phenomena we would expect.
All right.
Yes.
So as far as anharmonic oscillator is concerned, do you have any specific potential to consider cubic term or fourth term like that?
Yes. Here I consider this like factorization of the square. I didn't, well, for higher powers, yes, you can do it. There is a reference also in which they had this, I think it's quartic or sextic potential, which is quasi-exactly solvable. And they have found something in the time-dependent regime. That's something I haven't explored personally myself, but yeah, that's something that we can implement to these polynomial potentials indeed. I mean, you can do all this machinery, and I'm pretty confident that this can be done. The only problem with these quartic or higher order potential is that most of them, or all of them, are quasi-exactly solvable at most. So that's the only trade-off using those. But yeah, they can be used indeed.
Very interesting talk, Dr. Silasa. Very interesting talk.
Okay, thank you very much.
So any other question from the audience? All right, I'm not getting any questions.
Okay, so I would like just to remark something about Caldirola-Canay. And one of the reasons of this problem in Caldirola-Canay, now I remember your question, you may notice that when time is much larger than 1/kappa, this mass tends to zero pretty quickly, right? So this is one of the odd behavior that this quantum model has. So this is actually why in this paper I introduced this constant mu0, because this avoids the system, or the mass of the system to go close to zero. I mean, technically speaking, in Caldirola, it never goes to zero, right? But it gets pretty close, and this produces a large several odd phenomena. So this was one of the reasons in this paper I introduced this constant m0, because I say, well, it's kind of trivial, right? I have this constant. The problem is that the solutions are not so simple, because in the Caldirola-Canays are just exponential, and in this case involves hypergeometric functions. But well, the physical motivation of this mu0 is precisely to avoid that the mass approaches to zero so closely, even for large times. And yeah, this is one of the motivations of this Caldirola, just to clarify your question.
Because this is one of the problematic things as far as quantum mechanics is concerned, this damped harmonic oscillator.
Yes.
Yeah. Okay. So, since there are no more questions, I would like to conclude the session by thanking Dr. Kevin Silasa for accepting our invitation and giving a very interesting talk on solving time-dependent quantum systems.
My pleasure.
Yeah. Thank you very much, of course. Thank you.
Well, see you all later. Thank you very much. Bye. Take care.
Bye.